So now we solve the deflection and slope of our beam for the first case right here. How about for the second case, which is beam number 2? So let's do beam number 2, calculate for slope, calculate for the slope of our beam using point 2 and deflection of our beam using beam number 2 right here. So let's move to number 2. So number 2, we have this type of loading. So we have this, this reaction here, we have rollers here, and then instead of distributed load, now we have concentrated load, which is 150 kilonewtons, and that's located at x is equal to 2 meters, so it's this distance right here. Now, if you're going to solve for this problem right here, you are going to get this number, which is dy. Oops. Okay, so we have dy dx. So that's for the slope of your beam at point D, which is equal to negative p L square over 32 EI. And for deflection of your beam, that's y sub d is equal to 3 EL3 over 256 EI. Now, this is not really E, so let's correct that one. So that should be for concentrated load. So let's correct that, so that's not for exactly for D. So let's call it for concentrated load P at point D. And then this is for concentrated load P at point D of your beam. Now, how can we solve this problem? Now, we can cut our beam, use a second order differential equation. We can get the equation of our elastic curve. Same for the equation for the slope of the beam. Now, these are the answers, but let's just see how we solve this type of problem. So because the thing is, if we think about the second order differential equation, what we could do is we can cut our beam right here. And then we have a moment function, or we can cut our beam at this specific point, which has a different moment because we are excluding and including this concentrated load when we calculate our M as a function of X. So let's see how can we calculate these numbers right here before we actually put numerical values for slope and deflection. So how can we solve this one using second order differential equation? So for second order differential equation, so we need to cut our beam and perform all those integrals there. So let's do that. So again, we have our beam. We have support reactions at A and B. So we have AY, and then you have BY. And then you have concentrated load, which is P. And remember, this is L over 4. And this is 3L over 4. So imagine if we look at our slides. Oops, okay. Just going to drag it here. So what do we mean by L over 4? This is 8 right here. And that's 2, which means your load is located at 1/4 L, which is the same case here. Now 3/4 L, that's from this guy right here, that's 6 over 8, that's 3/4 L, and we can assume our L is equal to 8. Now we are putting L values right here so that we can apply this formula at any length L. In this case it's 8, but in our case let's use L, so that this could be used for different lengths of our beam. Now, if we're going to assume that this is P. Again, we are given with P, which is 150 kilonewtons. In this case, let's assume it's P. Your AY would be equivalent to 3 over 4P. Your BY would be equal to 1/4 P here. Now for second order differential equation, remember that we have to cut our beam. Now the problem with this is once we cut our beam, so let's say I'm going to cut somewhere here before my P, or I could also cut somewhere here, and that's a different story. Now if I cut using my section, let's call it 1 and section 2, I'm going to have different moment equation as a function of x. Now, in order to solve this problem using second order differential equation, so first let's divide our beam. So this is point A, this is going to be point, so that's B for sure, and then let's call this section as point D because we are asked to calculate at point D. Now the first section would be from A to D. Let's go back here. So that's from A to D. Now from A to D, we can assume section 1. Now for section 1 right here, so we have this. We do not have our P right there, so we have this. We have, oops, I accidentally pressed the, okay, so we have, this is 3 over 4B. And here, this is your shear. We cut our section, and that's going to be our moment. And let's call it M1 because eventually we're going to have M2 when we do section number 2. So actually we can even call this one as our V1, but right now we are interested with our moment. Now for section A to D, we get the moment at this point, and then note that this is our X for this specific section. Again, this is just for AD right here. Now, if we calculate for our M1 would be equal to 3P over 4X. Now, we have a moment as a function of X. We can now use our second order differential equation. Now, if we apply our second order differential equation, that's going to be EI d squared y dx squared, and that's equal to 3p over 4x. We have to integrate twice, so we're going to get here, let's call it y sub 1, because again, we have two sections right here. This sections from A to D and sections D to B. Now let's integrate. So the first equation that we have is, again, its slope EI. Now we have now just our slope dy over dx is equal to 3 over 8p x squared plus c1. So that's the first equation that we have. So after integrating this equation right here. Now we can integrate it further, so we're going to get EI. Now, again, that should be Y1, sorry, that's Y1. So now we have Y, that's the deflection of your beam, 1/8 Px raised to 3 plus, now it's C1x plus C2. Now we have two equations here, let's call it 1 and 2. Now we can take C1 and C2, apply boundary conditions, but before we do that, let's look at our second section, which is section 2, right here. For section 2, so we are looking at D to point B. So that's D to point B, and then we are using section number 2. So now I'm just going to highlight this one so that we can divide the two sections here. So that's from D to B. That's D to B. Now, that's going to be a different thing in terms of taking a moment from your section. So if we're going to take a cut from our beam, it's going to look like something like this. So we have from point A, we have 3 over 4p. We have our p, which acts at L over 4. And then we have our shear, and then we can have moment. We can now call it M sub 2. We can even call this one as V sub 2 right here. And then this is going to be the value of our X. So this whole thing here. Now, if we're going to get our moment, so moment at this point, so from this point up to 3 over 4p, you have length x. How about if we're going to calculate for the moment produced by p right here? So that's going to be x, which is your length, the length of your whole beam, minus L over 4. Then you can take the value for your p, which means that if I'm going to do that method, I'm going to get the equation of my moment, which is, we can call M2. M2 now becomes 3p over 4 x minus p x minus L over 4. So that's going to be the equation of my moment. Now we have equation of the moment. We can now integrate our function here. Now we can integrate it twice. We generate two different constant of integration. So in this case, we can use the second order differential equation again. Squared. Now this is y sub 2, because that's a second moment equation, d to b. And this is dx squared. And that's equal to 3p over 4 x minus p x minus L over 4. Now I can integrate this equation here to y so that I could get the equation related to the slope of my beam, related to deflection of the beam. Now if I'm going to do that, I'm going to have the following. So first, I'm going to get E I dy2 bx, so that's the slope at section dB, and then that's negative 1 over 8. It's negative 1 over 8 p x squared plus 1 over 4 p lx plus c3. Now, note that I combined something here. I combine this two here. Now, I have this equation with C3. I use C3 instead of C1 and C2 because I already defined that the value of C1 is from this equation. That's the value of C2. Now, I have C3 right here. Now, I can, again, integrate this function here so that I could get y2. So I have EI. Now, this is y sub 2. And now I'm going to get this number here. That's negative 1 over 24. It's p x3, so it's 2 there, plus 1 over 8 pl x3 plus c3x plus c4. Now I have 4 different constant of integration using my second order differential equation. It's because when I cut my beam, I have 2 different conditions here. So it's either I will include P when I cut my beam, or I will exclude it. Again, this is divided into section AD, and then now we have section DB right here. So how can I solve this problem? So I have now 4 different constants of integration. So C1, C2, I have C3 right here, and C4. Now we have to use boundary conditions. What boundary conditions I could use? So at boundary conditions. So first is we have x is equal to 0, y is equal to 0. I can also use second boundary condition, x is equal to L. Let's call it y1. Second boundary condition, x is equal to L, y2 is equal to 0. And then I'm going to use a third boundary condition, which is at x is equal to L over 4. That's the location of your P. That's the critical position wherein you may or may not include your P when you cut your beam. And we assume that at that specific point, the slope of your beam on the left side and on the right side is actually equal. So we have dy squared 2 dx. And we have a fourth boundary condition, which is at x is equal to L over 4. We have equal y1 and then y2. So we have equal displacement of our left beam and right beam because we are talking about exactly at point B. Now, if we are going to substitute the boundary condition number 1, x is equal to 0, y is equal to 0, so we have to use this equation right here. So that's y1. Take note, it's y1. X is equal to 0. If you go back to your beam, we are talking about at point A right here. So that's x is equal to 0, which means we have to use y1. So we should not use this one because this is for y2. We have to move back here. So we have to use this equation right here. Now y1 is 0, x is equal to 0. That will lead us to C2 is equal to 0. So from this boundary condition, I could get C2 is equal to 0. So now one of the constant of integration has been solved. Now let's look at the second boundary condition. X is equal to L, y2 is equal to 0. Again, x is equal to L, we are talking about the end of our beam. If we move back here, so we are talking about x is equal to L, we are talking about point B, which means we have to use section DB. And section DB is this DB right here. If we move back there, that's going to be y2. So using boundary condition number 2, x is equal to L, so those becomes L. We have a y2 is equal to 0, so this becomes 0. What we will get here is if we substitute those numbers, we have the following equation. So we're going to get 1 over 12 PL raised to 3 plus C3L plus C4 is equal to 0. So let's leave this equation as it is for now, and let's move to, because we have C3 and C4 there, so let's leave it as it is, and let's move to our third boundary condition. At x is equal to L over 4, that's exactly the location of your load. And we have the slope of the beam, left and right, they are equal. So what we could do here is check our equation. So we can now look at equation. If we look at this guy right here, that's the slope of our beam. Where's the equation for your slope? It's this guy right here. And then we have another slope right here, which is this guy. So I call it 1 and 2. I can call that equation 3 and 4 so that you will not be confused. So let's call it 3 and 4. I can now equate 3 and 4 for this boundary condition. So I can equate I can equate 1 and 3. what I'm going to get if I equate 1 and 3 are the following. So if I equate that one, you will get this specific equation, which is 3 over 128 PL square plus C1 is equal to 7 over 128 PL square plus C3. So you have C1 and 3D right there. So let's leave the equation as it is and move to boundary condition number 4. So for boundary condition number 4, we have y1 is equal to y2, which means if we go back to y2, so this guy here, number 4, and that's also the equation number 2 right here. So we can equate equation 2 and equation 4. So here we can equate equation 2 and equation 4. And then we will get the following once we equate those slopes. So we're going to get P L raised to 3 over 512 plus C1 L over 4 is equal to 11 PL raised to 3, 1536 plus C3 L over 4 plus C4. So you have C1 and C4 right there. So as you can see, we have C1, C4, C3, C1. So we have 3 equations right there, 3 unknowns, actually 4 unknowns because we have the first one as C2 is equal to 1. And once you solve those constants, you're going to get the following. So again, this is for equation 4 unknowns. And then you will get C1 is equal to negative 7PL square plus 128. C2 is equal to 0. C3 is equal to negative 11PL square over 128. And then we have C4, which is equal to PL3 divided by 384. Now we have those constants, and then we can now substitute it back to the equation. Now, but that's not the question right there. The question is what would be the deflection at point D. So we can substitute x is equal to L over 4, and then eventually we will get this equation right here, which we defined above. Okay, so which is this guy right here. Now I just showed you how to calculate those. Okay. So and then you will eventually get this guys right here. I just showed you how to calculate this one, but this must be covered from our previous topic, which is a second order differential equation. It's just in this case, you have 2 different moments that you have to consider when you cut the beam. Now we have this values right here. Slope of our beam, that's a deflection. And then now we can substitute the values, which are P is equal to 150 kilonewtons. And then you have L, which is 8 meters. And then you have x is equal to 2 meters. Now, if you substitute those numbers right here, you will get dy dx, and that's from concentrated load at point D. You will get, so that's 150, that's 8. This is 100 right here, and then you will get negative 3 times 10, negative 3 radians. Now for deflection, which is yp, caused by your concentrated load at point D, that's equal to negative, that should be negative, I think. That should be negative. That's negative 3 PL squared, 256 EI, We're going to substitute 100 right here. We have our P, we have our L. And then eventually what you will get here is negative 9 times 10, negative 3 meters. Now you have these values right here. Let's go back again to what we did previously. Again, we are discussing method of superposition. So just to recap what we did so far, we have our original beam right here. We split it into two. We calculated the slope of our beam, the first beam right here. We calculated the displacement at this beam right here. And then we calculated our specific slope of the beam at point D. That's the displacement at point D for this beam. Now we can add those numbers to get the final answer. So let's do that. So now we have this number right here, this number right here. So what would be the final slope of our beam if we have this complicated system? So the slope of our beam, which now we define as dy or d, so that's equal to, so I'm going to write here, so dy dx at point B is equal to, so let's look for the values that we solve caused by distributed load. So here, so we said earlier that the slope of the beam is this guy right here. So it's negative 2.93, 2.93. So it's negative 2.93 times 10, negative 3 radians, plus, so plus, because we are now looking at second term. Now I think that's in the last portion here. So it's a bit fast. Last portion, we have, oops, it's not here. So we have 3 times 10 raised to negative 3 radians here. So we're going to add it there, negative 3. So that's negative 3 times 10 to negative 3 radians. And then we're going to get a value which is equal to negative 5.93 times 10, negative 3 radians. So that would be the final answer for slope of your beam. So I'm going to change it into green. Now, if we're going to calculate for y sub d, so y sub d is equal to the deflection caused by your distributed load, and we calculate it down here, and that's this guy over here, this one. So it's negative 7.6 times 10 raised to negative 3 meters plus, so this is caused, the second term is caused by concentrated load P. So we did that down here. So we have a number here which is 9 times 10 raised to negative 3, and that's a negative number. So that's a negative 9 times 10 to 3 meters, and we can add them together, and then you will get 16.6 times 10 negative 3 meters. So that's going to be the answer for y sub d. So now we are finished discussing the method of superposition. Again, from a complicated system, we can split it into two simple beams, and then whatever the slope or deflection at those points, we can add them together, which are defined in this lecture right here. Okay. I'll just move it around. So now that's for statically determinate beams. So what if we have statically indeterminate beam, which is a bit of bit long. So method of superposition, statically indeterminate beams. So as we discussed previously, if we have, let's say, a cantilever beam, we have additional support reaction, in this case, point B. So we have three reactions at A, we have at X, at Y, moment at A, and then we have another reaction which is B sub Y. So we have indeterminate beam, and how can we calculate for this specific beam? So for this problem, I'm just going to show you how this one works. So, okay, let's go back to our board right here. So now, so determine the support reactions at A and B. So how can we solve this one? So let's say we have a cantilever beam. Yeah, that's cantilever beam. So that's support reaction B. We have a roller here. How can we use method of superposition if we have this type of problem? We can split this beam into two. What do we mean into two? So we can have just the cantilever beam, and then the other one is with the first one would be cantilever beam with your distributed load, and the other one, it's just a support reaction at B. So let's do that. So we have here, which we can split into two. So we have this beam. Sorry, it's not scaled, but let's assume they should have the same length. So that's distributed load. So for the first beam, we remove the support reaction there. And for the second beam that we have, we remove the load and we only have the support reaction R. So let's call it B sub Y. So now we have two different beams. So we have this, which is a very simple beam to calculate. We have this system right here. For this beam right here, so we have 1 and 2. So I'm just going to change my pen. So that's 1 and number 2. So if you look at the beam, this is a cantilever beam, which I think we solved in our previous lecture. So how can you, for example, calculate the equation of elastic curve? So we have distributed load, so we can use fourth order differential equation. So in this case, so let's say we can use EI B 4 YD X4 is equal to negative W sub X. We can use the fourth order differential equation. We're going to get the equation of our elastic curve. Now, once we get the equation of elastic curve, that's as if we have equation as a function of X. And the length of our beam, we can define it as L. Now, if we get the equation of our beam or deflection at point B, so let's call it point B, in this case. So we are going to get Y caused by distributed load at point B is equal to negative W L4 over 8EI. Again, this is from your previous lecture. So in order for you to get this equation right here, you can use fourth order differential equation and then integrate it 4 times, get C1 up to C4, substitute those constant into your equation, which is for deflection. And then once you have that equation, you have X right there. Substitute X with L because we are talking about at specific point B, and then you will get this. Now, same thing for this for beam number 2. So in this case, you can get the equation of your elastic curve by using second order differential equation, which is EI E squared Y dx squared is equal to M as a function of your X. Now, how this process works, you can cut your beam, and then you can get all those moment as a function of x, and then eventually you will get the equation of your elastic curve. What do you mean by equation of elastic curve? That's y as a function of x, and then let's say you want to get deflection at point B, which is at L. You have to substitute L to your x. Now, once you do that, you will get, so I'm going to call it y, that's for support reaction R at point B, is going to be equal to RB, not RB, let's call it BY. Okay. Oops. So we have BY. Oops, it's not working. Oops, sorry. We have BY. So that's reactions at point B. L raised to 3 divided by 3EI. So we have this equation for our deflection at point B. Now, similar thing with the previous problem. So we can say that deflection at B, given this system right here, is equal to deflection of our first beam plus deflection of our second beam. And in this case, we can say that YB is equal to negative WL4 over 8EI plus, it's RB, L raised to 3EI right there. Now, the thing here is, if we are looking at YB, and that's this point right here, YB should be equal to 0, right? Which means this equation right here should be equated to 0. So based on this equation right here, the only unknown right here for support reaction is RB. In this case, we can easily get RB, which is now equivalent to 3 over 8 WL. And that's going up for support. So now we have this RB right here, which is, should I call it BY there? Sorry, that should be BY. Anyway. Okay. So now let's call it BY. So this is going to be BY right there. So that's going to be the number for your BY. Now, how can I get the other numbers? So we have summation of forces along Y is equal to 0, which means I'm going to get AY plus BY minus WL is equal to 0. So where did I get my WL? That's the distributed load right here. So it's this guy right there. So that's your WL. And once I do the summation of forces along my Y direction, eventually I will get AY is equal to 5 over 8 WL, and that's going up. Now for your moment at A, because you have a cantilever beam at point A, you have a moment, so I can sum my moment at A, which is equivalent to 0. So I'm going to get moment at A plus BYL minus, that's the distributed load, that's the location of your distributed load, which is the center of your beam, and that's equal to 0. So this is L. It's because if we go back to our beam, it's located at L right there. Now eventually we're going to get MA is equal to 1/2 WL squared, and that's rotation right here. So now there's another reaction which is at X, but that's 0. So we have AX is equal to 0. Eventually, we have now calculated the support reaction. So we have AX here, we have MA right there, we have AY, and then we have BY. So again, just a recap of what we did for indeterminate beams. So we have this indeterminate beam. We split it into two. So first, we took the distributed load. We removed the support. We took the distributed load. So we have the first beam right here. And then, for the second beam, again, we have a cantilever beam. We now disregard the distributed load, put in the reactions at By. We assume that it's kind of force that we are separating. One is distributed, one is concentrated. And eventually, once we separate these two, we can use a second order or fourth order differential equation, both of them, to get the deflection at Y. So we have this equation right here. And then once we have that one, we can now get specific reaction right here. So I think that should be By. I'm just going to change it. Sorry, guys. That should be By. And keep using RB. So that should be By L. And then eventually you will get this number here. And then you have all the support reactions. So that's how you use second order, fourth order superposition if you have indeterminate beams. So for example, in your exam, I might specify what method you have to use. But some problems, I will just mention that you can use whatever method you can. But I'll give you instructions for your exam. So that's the end of this chapter. So the next lecture will be about columns. And thank you. I'll see you on the next lecture.